Drop a pebble into a still pond, and you will immediately see a series of concentric circles rippling outward from the point of impact. It looks exactly as if the water itself is flowing away from the center. But if you place a few pieces of cork on that disturbed surface, you will notice something specific. The cork bobs up and down, but it does not drift away with the rings. The water mass remains right where it is. What you are watching is a moving pattern of disturbance. Energy and information are propagating from one point to another without any actual physical transfer or flow of the matter itself. That is the exact definition of a wave. This creates a unique problem for physics. We need a mathematical framework to describe an event where the medium stays in place, while a distinct pattern continuously travels through it. In simpler mechanics, we often study objects oscillating in isolation. But a wave moves through a material medium, where elastic forces bind every microscopic constituent to its neighbors. The motion of one particle instantly affects the next. If we take a photograph to freeze a wave in time, we only capture its overall shape in space at that exact fraction of a second. We lose all information about how fast or in what direction the disturbance is traveling. Conversely, if we focus a camera tightly on just one single segment of a string as it moves up and down, we record its motion over time, but we lose sight of the massive wave pattern stretching out across the entire medium. To accurately describe a traveling wave, we need a mathematical function that tracks both position x and time t simultaneously. We need the master coordinate system, y of x and t. Let's isolate the spatial geometry first. By setting the clock to 0, fixing time at exactly t equals 0, we can examine the physical shape of the wave. This plot displays the displacement along x-axis as a simple sine wave. If we measure the physical distance between two consecutive crests, or any 2 points in the exact same phase, we find the wavelength, denoted by the Greek letter lambda. From this, we derive the angular wave number, k. This is calculated by dividing 2 pi by the wavelength, giving us a standard measure of how many wave cycles can be accommodated per unit of distance. This spatial term, kx, dictates the physical repeating structure of the wave across the length of the medium at any given instant. Now let's look at the inverse perspective. We lock our attention onto a single fixed location, say the origin point at x equals 0, and let time run forward. This diagram tracks a single particle isolated on the y-axis. It is not moving forward. It executes simple harmonic motion, oscillating vertically from its equilibrium position. The exact time it takes to complete one full cycle of this up and down motion is called the period, t. This cycle generates our angular frequency, omega. Omega is equal to 2 pi divided by the period, which is also equivalent to 2 pi times the standard frequency, nu. Nu simply measures the exact number of oscillations per second. The temporal term, omega t, acts as the internal clock for the wave. It strictly dictates how fast every individual microscopic piece of the medium vibrates. Combining space and time gives us the complete displacement relation for a progressive wave. Yxt is equal to a sine kx minus omega t plus phi. Here, a represents the maximum amplitude, k is the wave number, and omega is the angular frequency. The entire mathematical argument inside the sine function is known as the phase of the wave. The symbol phi represents the initial phase angle at x equals 0 and t equals 0, allowing us to perfectly align the equation with wherever the wave physically starts. Because of this initial phase angle, the single sine function can equivalently be broken apart into a linear combination of both sine and cosine functions. They mathematically map the exact same physical reality. This single line of mathematics solves our initial paradox. It completely unifies the localized stationary vibration of matter with the continuous global movement of energy across space. To measure how fast this energy is actually traveling, we have to track a single point of fixed phase, like the very top of a wave crest, as it pushes through the medium over time. This graph tracks 3 successive wave profiles at t equals 0, a quarter period, and a half period. The particle at the origin moves strictly up and down, but the crest itself continuously shifts to the right. For the exact phase of that crest to remain a mathematical constant as time increases, the position x must also increase proportionally. The rate of this necessary shift is the velocity of the wave. By tracking this shift, we find that the speed of any progressive wave is simply the ratio of its angular frequency to its angular wave number, v equals omega divided by k. This relationship also dictates which way the wave is moving, a detail entirely controlled by a single mathematical sign. When we look at the standard wave equation, the phase contains a negative sign between kx and omega t. But we can also write the exact same equation with a positive sign. In the equation with a minus sign, x must grow larger as time moves forward just to keep the total phase constant. This mathematical necessity physically drives the wave pattern forward in the positive x direction. Conversely, if there is a plus sign between the terms, x has to decrease as time increases to maintain that constant phase. That single plus sign forces the entire wave pattern to propagate in reverse, into the negative x direction. In a progressive wave, the disturbance travels while the medium remains anchored. This physical duality is perfectly encoded in the combination of x and t within the displacement function. With this single expression, we can calculate the exact position and motion of any individual constituent in a system, whether it is a stretched string or a massive column of air, at any millisecond in the future. The displacement relation gives us a unified mathematical language to map how energy moves through the universe, from the sound of a voice to the light of a distant star.